time, you guys, we did the Chapter A test. Overall, things went pretty darn good. So those grades I posted this morning. If you took it on time, that's posted this morning. Overall, they're quite good. So nice job, everyone. Today, we're going to be talking about Chapter 12. So the first thing we're going to be talking about in Chapter 12 are polynomials. So that was something you guys talked about last year, right? In Algebra 2, polynomials and polynomial functions. So we'll just kind of start by recapping the definition for a polynomial. So a polynomial is just something that can be written in this form, which seems kind of a weird way of writing it because that looks like a lot of letters. So what's going on here with all these letters? Well, these guys are just the leading coefficient, right? They're just coefficients. So all those AIs are just real numbers. So anything like 2, 1/2, square root of 17, pi, like all those things are real numbers. That's any of the A's could be any of those things. There is one catch though. A sub n can't be 0. Yeah. So just the polynomial starts, it can't start with a 0 term. That's fine, whatever. And then the other piece is that we have these exponents, right? Those exponents have to be, okay, the whole numbers, yep, and, well, non-negative, right? Because 0 is okay. Yeah. So we mean like 0, 1, 2, etc. Okay. Everybody's okay with that? So if we locate the x with the biggest exponent, and we talk about that whole term, we call this guy the leading term. The coefficient on the leading term is the leading coefficient. And the exponent is going to be the degree for the polynomial. Okay, so those are the three kind of key pieces of vocab when we talk about a polynomial. So let's do a couple of examples. We're just going to identify whether something is a polynomial or not. And if it is, we're going to list the degree for the polynomial and the leading coefficient. All right, so here we go. I got 4 examples here, starting with example A. Is f of x a polynomial function? Yes. Great, I agree. Notice that the only operations that are going on is like we're multiplying a whole number or a constant to our x's and then adding or subtracting terms. All the exponents are positive whole numbers, or I should say non-negative whole numbers. So definitely a polynomial. What's the degree for the polynomial? It is degree 6. I notice the biggest exponent is a 6. And the leading coefficient is 4, because that's the coefficient on the biggest degree term. Great. Let's look at B. Is B a polynomial? Yes is correct. Now notice that the square root is ending at the 3. The square root does not extend over the x. Everybody see that? The square root extended over the x, would it be a polynomial? No. So you have to be very careful in reading that. What's the degree for this polynomial? 1, because that's an x to the first. And the leading coefficient is? Square root of 3. Great. So C is no. What's wrong with it?
Square root all the way over.
Yeah, the square root is going over the x's. So that's going to be a no right there. Since it's not a polynomial, we can't talk about its degree or leading coefficient. How about D? Is that a polynomial? No, why not?
-1 is exponent.
Yeah, we have an exponent that's a negative value. Great. And again, since it's not a polynomial, we don't talk about degrees and leading coefficients. Everybody okay with that? We have some special names for polynomials. And oftentimes we'll name a polynomial by its degree. So we have 4 special ones that I would expect you to remember the names for, but they're probably things we already kind of know the name of already. Drop this in. Save me some writing. So if I have the polynomial f of x equals 0, that is degree undefined. And we call that guy just the 0 function. If I have f of x equals a, where a is just some constant, it's not 0, that has degree 0, we call that a constant function. If I have f of x equals ax plus b, what does that look like? Ax plus b? Yeah, slope-intercept form, right? That's a degree 1 polynomial and a linear function, because what kind of graph does a slope-intercept equation make? A line, right? Hence a linear function. And then, don't do that one. We have ax squared plus bx plus c. I know it's at degree 2. And again, last year you talked all about things that looked like this. We called those guys quadratic functions when they're degree 2. Guess what? We just did the first section. Like that's it. Chapter 12 is like a big nothing burger of a chapter. Okay. 12.2 is about correlation. So when we talk about correlation in mathematics, we're really specific. So when we talk about correlation, we mean, is there a relationship between two quantities? Now, we're not assuming it's a causal relationship between the two quantities, like you might in a English language sense of the word. Mr. Kulik, can you give me an example?
Mr. Cook, can you give me an example?
Sure. You guys seen any tigers around in this room?
I haven't seen one yet.
So I would say that the presence of this stapler perfectly predicts the presence of tigers, right? So clearly this stapler is causing a strong tiger repellent field. That makes sense to you?
No.
No, right? There's correlation between the presence of tigers and the stapler, but is the stapler causing the deterrence of tigers? No. It has more to do with there being like, there's no tigers in America. It's not a native animal. Unless you go to the zoo or something. You're not seeing a tiger or just walking around.
We're going to Canada's house. You got to do it.
Oh, you're a crazy guy then, huh?
Yes.
All right. So when we talk about correlation, we're just talking about like the strength of the relationship between two variables. Okay. So let's think about something that another kind of common quantity, something that's easy for us to conceptualize, that is closely related. Let's say like the height of a person and the weight of a person. Right? Taller you get, on average, the heavier you're going to be. Right? More or less. Okay? Especially if you compare like a 3-year-old to an adult. Right? A lot taller, a lot heavier the adult is. So what are we noticing there? As weight goes up, or as height goes up, weight goes up, right? And we'd probably say that the height would be the independent variable and the weight would be the dependent variable, right? As your bones are getting longer, they're also getting heavier. Your muscle, you need more muscle to support the bone. Everything gets that, it's the weight that depends on the height. So we let's talk about what like a strong correlation looks like, or a weak correlation. So just some kind of vocab-y stuff. So let's say that we go ahead and make some measurements and we plot some data. So if I look at the first plot, this data looks rather like a line, right? It's pretty closely grouped together in the shape of a line. We'd say that's strong correlation. We might even say this is strong positive correlation because the line has a positive slope. If I look at the second data set, again, that's kind of a line, but the spread, the distance that data points are from the line, is much larger, right? We'd say that's weak correlation, and we might even add the word negative in there because the line that this data most closely resembles has a negative slope. Is everybody okay with that notion? Now, this line that I kind of sketched in here is what we call a best fit line. Yep. So I made an approximation of that, but I basically just tried to draw a line that was as close as possible to all of the data points. Okay? So I tried to draw it as close as I could to all of the data points. Now, the measure of our fit, or what we want to do is we want to like make this a little bit more quantitative, right? So we want to talk about, okay, can I numerically describe how good the fit is in the first graph versus the second graph. Everybody's okay with that? So the number we use there is called the correlation coefficient. And we abbreviate that with the lowercase letter r. And that correlation coefficient is a numerical representation of how closely data fits to a best fit line. So properties for the correlation coefficient is it exists on a continuum from -1 to 1. So at 1, this is like perfect fit, meaning that all the data points in my sample would actually be points on the best fit line. And -1 likewise also means a perfect fit. If the R value is negative, it tells you that the correlation is negative. If the R value is positive, it tells you the correlation is positive. The slope of the best fit line would be positive. And then as we get closer to 1 or -1, the correlation is getting stronger. So when we're very close to 0, we would say there's no or very, very weak correlation. At 0 exactly, we say there's no correlation. Now, 0 is kind of a theoretical value. If you actually do a sample, unless the sample is absolutely perfectly random, you're not going to actually get a 0 R value. In practice, that never happens. It's kind of a theoretical value. But the closer you are to 0, the weaker your correlation is. Typically, strong correlation ends at 0.7-ish or and above. We'd say is strong. The closer you're getting to 1, the better. Really, if you're trying to do any kind of prediction, I'd want something, 0.95, if it really my life depends on it. So let's just take a look at a picture, and we're just going to kind of use our eyes here for a moment. So what do you guys think here? So it is negative correlation. We can see that because, again, any best fit line you draw, it's going to kind of have a negative slope. Now, what do you think? Is this going to be strong or weak?
Strong.
I would agree. Yeah. What if instead of giving you a graph, we're given like a table of data? So one way you could do this is to graph it and take a look and make an estimation. What if I told you your calculator can give you the numeric value for R?
That would probably be pretty awesome.
Yeah, it can. Let's run through how to do that. And in fact, what if I told you your calculator can plot this data for you as well?
That was probably second.
Yeah, that would be nice also. So let's show you guys how to do all of that stuff here. We'll plot the points first, and then we'll show you how to get the R value second. Sound good? We're going to plot the data on our calculator first, and then we'll use the calculator to get the R value second. Either one of these would be appropriate ways to answer this question. So to enter data into my calculator, to enter this table of data in my calculator, I'm going to start by pressing the Stat button, which is right next to the left-hand arrow. We're going to choose the Edit command. So I'm going to press Enter. And I'm going to note the names of the two lists that I'm going to be using are L1 and L2. As you entered this stat menu, did anybody have data already there? Okay. Let's just pretend you did for a second. Let's say I'd like the numbers 1, 2, 3 there. If I make a mistake and I want to get rid of one of those entries, it's like, oh no, I typed an extra one here. You can press Delete and it'll delete a single entry. Or if I wanted to get rid of everything in L1, what I can do is I can move my cursor up to L1, and I'm going to press Clear, don't press Delete, and then the down arrow, and it'll wipe the entire list. So clear and down when you're on the title. All right. So here we're given a list of prices for a can of food, and then the number of cans sold at the store. Which one of those do you think is the deep or the independent variable? Which one depends on which? So the number sold depends on the price, right? We'd expect more, you sell more the cheaper it gets. Everybody agree with that? So the price is going to be our independent variable, like our X coordinate. And the number of cans sold would be like our Y coordinate, our dependent variable. So I'm going to type in the price per can first. So I don't need to worry about the 0 on there. I'm just going to point, or 2.5 is good enough. And I'm just going to type these in one at a time. Again, 2.00. I don't need to worry about the 0.00 because the calculator is just going to drop it anyways. So I did that. And I'm going to move arrow over to L2 and then type in the number of cans. And then before I move on, I'm just going to take a quick look and double check to make sure that I have the same number of things in L1 as I do in L2, so I didn't skip one accidentally. I'm just going to double check the numbers to make sure I typed everything in correctly. I didn't like fat finger a button or transpose two numbers or something. That all looked good to me though. Everybody's cool?
Yep.
Okay. I'm going to exit out of here, so that's second in mode to exit a menu. Then I'm going to go press second and Y equals to open the stat plot menu. And I'm just going to pick one of these plots. It doesn't matter. I have 3 options. I'm just going to pick plot 1. I'm going to start by turning it on. And then I'm going to look at the options. So the first option is the one I want, where it's going to plot individual points. So that looks good. I wanted to use the X coordinate as my stuff I entered in L1, which was the price per can. And the Y coordinate as the stuff I entered in L2. If, for example, I had entered something in L3, and I'm like, oh, I need to change that to L3. Notice above the numbers 1, 2, 3, 4, 5, 6 is L1, L2, L3, L4, L5, L6. So I could do like second and the number 3 to get the L3 to come in there. But that's not what I had, so I don't actually want to do that. Oops, not helpful, dum-dum. There we go. And then I like plotting the little boxes. I think they're easier to see than anything else. So I like that option. You're free to use whichever one, though. That's just going to be the shape the point is on your graph. Okay, now to get this thing to graph, I'm going to pick Zoom. Oops, I got to exit out apparently. and then pick zoom, and I want to pick zoom or Z-stat. Z-stat, oh, zoom stat, there it is, option number 9. So what zoom stat's going to do is it's automatically going to adjust your X and Y axes to fit the data in your table. Whatever stat plot you're using, it's going to automatically set your X and Y axes so that like you get a nice looking picture. Ooh, before that, I should have gone back to the Y equals menu and like checked to see if I had anything in there and gotten rid of it. I guess I could do that real quick. Yeah, I had gobbledygook in there and I got stuff in there I didn't want. Anyways, so this is my graph. That looks pretty good though, right? Yeah, strong negative correlation there. I agree. What if we wanted the R value though? So I'm going to exit out of the graph. I don't need the graph to get the R value. I do need the data in the table though. So if I hadn't typed the data from into the table like we did at the start, I would need to do that now. We've already done that, so I don't need to do it again. To get the R value, first thing I'm going to do is check something. So, and this is, once we've done this one time, you don't have to do it again. But we do need to make sure that a certain option is activated on our calculator. So the easiest way to do this is to press second and then the 0 button. That opens the catalog, which is just an alphabetical list of every command on your calculator. The command we're looking for is called diagnostic on. So you can either scroll all the way down to the D's, or if you look above the buttons in the green are letters A, B, C, D, etc. So the D is above the X negative 1. If I press that, it'll skip me all the way down to the D's, which saves me a lot of down arrowing. Diagnostic on is the option that I'm looking for. So I'm going to pause here while people are looking for it, but that's the option I'm looking for. So I'm just moving my cursor so that diagnostic on is indicated there. Once I found it, I'm going to press enter. That pastes it onto my home screen. And I'll press enter again, and it'll say done. Once we've done this once, unless you reset your calculator, your batteries die or something, you don't have to do this again. Okay? This was a one-time thing, unless you clear your calculator's memory, or your battery dies, or you're borrowing your friend's calculator who you haven't used before. But ideally, you do this once and it's done. Okay. So now that we've done that, again, wouldn't have to do this normally, but we're doing it once now. We're going to press stat. But this time we're going to go over to the calc option. And we're going to pick linreg. So what linreg is that the calculator is actually going to build us the equation for our best fit line. So there's like an algorithm that the calculator uses to create this best fit line. If you take a stats class, you'll learn how to do that. Beyond the scope of what we're going to do, we'll just let the calculator handle the heavy lifting for us. So I'm going to find linreg and press enter. I want to point out to you that there's 2 linregs. I don't know why they bothered to do this. The only difference is, look at the difference. The A is the coefficient on the X in the first one, and the second one, the B is the coefficient on the X. It makes no difference which one you choose. I just always choose the first one. All right. When I do this, a menu pulls up. So my linreg menu asks for, okay, where did you type in your X coordinates? Well, I typed mine into L1. So that was the default, so that's good. It says, where did you type in your Y list? Well, I did put that into L2, so that was the default. That's good. Frequency list. We'll never use in this class, so you can always leave the frequency list blank for our class. And the last question asks to store the regression equation that we're about to write. This I think I would like to do, because I would like to be able to graph this to look at my best fit line with the data that I have. Right? That would be a nice thing to do. So what I'm going to do is I want to store this into like either y1 or y2 or y3 or y4, something in the y equals menu. So when I graph, I can look at my scatter plot, my plot of points, with the best fit line at the same time. Everybody's okay with that? So I'm going to put it into y1 is where I'm going to put it. To get the y1, I'm going to press the vars button, which is just underneath the down arrow. From the vars menu, I'm going to move over to the yvars tab. And then from the 4 options here, I'm going to pick the function option. And then there's the y1. I'll press enter to select y1. So now I'm storing the regression equation for y1, or into y1. I'll move the option down to calculate and press enter. So here's my regression equation. It says it's y equals negative 104 and change x plus 329 and change b. And the r, the correlation coefficient, is 0.96. That's excellent, right? That's very close to 1. This is quite strong. If you press the y equals button now, you'll notice that in the y1 spot is that equation that it just showed us. The calculator typed that in for us automatically, which is lovely because that was a lot of decimal places to type in. And if you hit graph, now it'll draw that best fit line in with our scatter plot, and we can see it all at the same time. Is everybody cool with the calculator commands to get there? Okay. So what is the other benefit of a best fit line? What can we do with it though? Well, when you say find more points, what you're really talking about is making a prediction. We're not going to find actual data points with the best fit line, but it could predict how many cans we could sell if we wanted to charge, I don't know, like $1.80 or something, right? So there's 2 types of predictions we can make. The first type is called interpolation, and the other is extrapolation. Yes. What is the difference?
One is inside, one is outside.
Good. Yeah, let's just finish this thought and we'll go. Okay, so we'll pause here, come back and finish this after lunch. We're talking about correlations, right? We've been talking about this best fit line, and we can use a best fit line to make a prediction. And we said there's 2 types of predictions. There's interpolation, where you're predicting with an X value inside the data set. So for example, at $1.80, if I want to predict how many cans would be sold, that's inside the range of X values. And then there's extrapolation, where we pick an X value that's outside of the data set. Like if I want to predict how many cans I'd sell if I was charging $1, that would be extrapolation. Which one of these 2 is going to be more reliable as the predictions go? Yeah, interpolation will be more reliable. Why?
Because it's the best fit line extends to where this.
Yeah, basically. Imagine we did this, right? Let's take a bunch of kids like ages 5 to 10. We're going to record age and height. Okay? We're going to build a best fit line using that, and then calculate the height of a 100-year-old person. What are we going to get? Like a bonkers number, like a 10-foot person because they're 100 years old, right? Bad use of, because it's extrapolation, you're not getting a good prediction, because what do we know about people as they age? Well, they stop growing anyways, right? You get to 18 or so and you're really done growing. So like, not a great, won't be a great, even though like maybe our best fit line has excellent correlation, because we're predicting outside of the data range, we may not get a very good prediction. So let's talk about making good predictions. And there's really two things we need to have for a good prediction. What are the two things going to be? So we're going to be using interpolation, right? That's for sure. And what else? What's the first part got to be? We have a good model. What does that mean? We have high correlation, right? So the best fit line that we built has an R value that's close to 1 or -1. And then we interpolate with that model, we're going to get a pretty reliable prediction. If you have a garbage model, even if you do interpolation, you're probably not getting a good prediction out of it, because it's just not reliable, right? The R value doesn't say this is very linear, so I wouldn't expect reliably for a linear model to give me a very good prediction. That's basically the gist of it. So if we go back to that best fit line that we made here, and I want to say make a prediction, like I want to find out how many cans we'd sell if we charged $1.80. The easiest way to do this is we just want to plug $1.80 in for X, but we have all those stupid decimal points, right? So this is the easiest way to do it, is I'm going to press the vars button, going to go over to the yvars tab, select the function command, select function y1, and I'm going to do like parenthesis 1.8. So this is like function notation, right? Where we do like f of 1.8 min. We're going to plug 1.8 in for x's. This is going to plug 1.8 into the function in y1. So we predict, about 141 cans sold. Everybody's okay with that? And if I look at that, does that track? Seems like it, right? Yeah. $1.80 is, right around here. It's reasonable enough. What else would we do? Oh, what if I wanted to find out like how much I need to charge to sell like 300 cans? Probably the easiest way to do that would be going to the y equals menu, typing in 300, and double check my window, not tall enough. Maybe let's say, yeah, it's fine. So I got to make my Y max a little higher there, make 350 or something. Oh, I'm dumb, right? Oh, that's so dumb. What if I said we want to sell at least like 50 cans? Let's do that. There we go. I'll go back and just zoom stat that. So I want to sell at least 50 cans. Oh my goodness. So here's my line for 50. I'm interested in the intersection there. Probably might have to extend that out a little bit more. But I'm looking for that intersection. Second trace, intersect command, enter, enter, enter. So about a $2.67 I can charge and still sell 50 cans. That okay with you guys?
Solid.
Yeah. We're going to stop here for today. I feel like that's enough of 12. What can we do so far? You guys should be able to do to say 12. That looks good. Most of these problems are all stuff you're just going to use your calculator to do. So mostly it's going to be practice, like going and entering your data into the table, building a best fit line, using that best fit line to make a prediction. Pretty straightforward. I would strongly encourage you to try to do some of this now. So if you have trouble with the calculator parts, you can ask a calculator expert while you're here. And it's not a lot to do, right? This is pretty light in terms of writing. You're just mostly just typing stuff into your calculator and getting your calculator to do stuff for you. Okie dokie. Okay.